Hi, welcome back. So today's lecture will be about load line and different modes of operation. So basically, today we will focus a little bit on graphing. So let's learn about a pretty useful graphical approach to analyze our BJT. And at the end, we will study different mode of operation of the BJT. Okay, let's do it. Previously on Electronic 2, we went through this example together. So now I put the circuits back here. You can just refer to previous lecture as a reference on what we did with the circuit. But um, what I want is now today is I want to discuss some thought experiment. So if I plot two parameters on this graph here, on the x-axis I have small v, okay, VBE, that which is the voltage across this BE junction here, and IB, which is the current across this BE junction. Okay, that going actually the current going into the BE junction. It should be similar with this IB. However, you have to know that this IB current will change if this voltage change also. Okay, so now we want to study the relationship between these two values. So what do we know? First, let's try to examine different points that we know about this circuit. So let's assume at one point when VBE equal VBB equal 4. That means the voltage across from here to here, or the voltage at this point right here, because this is ground. Okay, the voltage at this point, if it's equal to voltage at this point. So this one and this one, the voltages are equal. Okay, if that happened, now I have VB equal 4. Then I have VB equal 4. So if I have two equal voltage level, there should not be any current flowing through, right? So then I can conclude that IB equal 0. So to draw one point on this plot, I can put a dot on it. Okay, that means no current, and when voltage is at 4 volt. Okay, what's next? Next is I also know about a condition called when the voltage across equal to VBE on, which is 0.7 volt. And I know that because I did the calculation from the previous example, from previous lecture. So I know that the current will be 15 microampere. So now I put a dot on the plot, okay, and on the y-axis it should be 15, okay. So now I have 2 points, right? With this 2 point, I can actually connect the 2 points together with a line, right? You can draw a line through 2 points. So I can draw a line, and on this plot right here, this point, it has a name. It's called Q point or quenching point. It's basically the characteristic of your circuit when VBE equal VBE on equal 0.7 volt. Okay, so this is one of the important point. And this line now is called load line. Alright, so there's a question in the beginning. If we have a line, usually we're trying to find the y-intercept. So what is the y-intercept of this line? So what's the y-intercept? So basically at this point, VBE equals 0, right? Because it's the y-intercept. So because VBE equals 0, if you refer to previous lecture, you know that if you want to calculate IB, which is this current, you basically use this voltage minus this voltage and divided by this resistance right here, right? So you put that equation in, but now VB equals 0, take it out, and you calculate this, and you have 18.2 microamperes. Okay. So what happens if you change the value of VBB or basically the base voltage and the base resistance RB. So I just copy and paste again the load line here. So technically, if you have a higher VBB, okay, the line will be shifted up like this, and if you have a lower VBB, it will be shifted down like this. You notice that I didn't change the slope because you can calculate the slope to be basically minus VBB over RB, and divided by this value in X VBB, so you cancel out the VBB, and you have the slope to be independent of the base voltage VBB. Okay, it's only depending on the slope is only depending on RB. Therefore, if I want to change RB, I can have a lower RB can give me this, and a higher RB can give me this. Okay. So now we just analyze the BE junction. How about the we just analyze the BE junction. How about the other junction? How about the other junction? So first, let's plot it out. Let's plot on the x-axis VCE, which is the voltage across, like commutator and like collector and emitter. Then IC is the current going into the collector. Okay, so if we plot it out, usually you can have this characteristic line like this. That means when you fix a base current, it will respond in one way. For example, if you supply a base current of 5 microamperes, you can increase the base, you can increase the collector the current of the collector in the first few 0.1 or 0.3 volt of VCE, but then when you keep increasing VCE, it will flat out. Okay, this value will flat out, and you can calculate that. And you can calculate your IC current, collector current also. So, and you all know that the relationship between collector current, which is the value of this pink line right here, is linear to the base current. Collector current is linear to base current because IC equal beta IB. But there's a catch, and let's talk about it later. So first of all, some of you may ask, how can you pull out this line from thin air? So let's just analyze it together. So we have this line here, and we're trying to analyze this loop right here. Okay. So in this loop, we can see that we have VCE equal VCC, which is this one. So VC is voltage across here. So technically, if you wanna calculate this, technically it's this voltage minus the voltage across this resistor. Okay, so I will have VCC and minus the voltage across this resistor. Using Ohm's law, I have IC multiplied by RC. Okay, so I have this equation right here, but I want to write it in the form of a linear equation with this is my y-axis and this is my x-axis. So I just rearrange everything, then I plug in the value to have my linear equation. Okay. Just a warning, this is the DC load line equation. We have a separate lecture for AC version of it. So there's a few things you need to know about mode of operation. Okay, so when you have VBB is less than VBE on, technically you are not powering your transistor enough. Everything should be turned off. There will be some leakage. We talk about later, but for this case, we're not gonna care about leakage. We assume that this is the perfect world. But yeah, in the cutoff mode, there's no current going through anything. Okay, so base current 0, collector current 0. But when you have your VBB, when you have your VBB is larger than VBE on, now you can power it on. Okay, you power your transistor on, then in that case you can see every time you increase IB, you actually increase the IC also. Okay, so increase base current, you can increase collector current. However, you can only do this up to 1 point. You can only do this up to 1 point. Then basically your transistor can be in saturation mode. So there's a dot line here. In the saturation mode, basically if you keep increasing IB so much, IC will fail to catch up. Okay, so collector current will fail to catch up, and now the relationship between collector current and base current will not be linear anymore. So that is a rough definition of saturation mode. So we basically cover mostly three mode of operation, right? We know what's the cutoff when no base current, no collector current. We know the forward active is when basically base current, the collector current increase linearly with the base current increase. And finally, it's the saturation when you increase the base current so much you increase the base current so much you cannot, the collector current cannot keep up, so saturate. So another mode, the last mode of operation is called inverse active. Okay, and the inverse active mode, in this mode, basically the B junction is reverse bias and the BC junction is forward bias. So basically it's reverse. Okay, so basically the transistor is operating upside down. Okay, and the emitter is acting as a collector, and the collector is acting as an emitter. So you flip the role of collector and emitter, then you will have the inverse active, and everything should be the same with the forward active. Okay. Okay, so we are at the end of our lecture today. So next time I will try to cover BJT amplifier. Some of you may ask, why do we need to do the practice 5.5 first? Actually, it would be more logical to try to do the example 5.4, and you can move on to the example 5.5, but I want you guys to just tackle out 5.5 first because it's a pretty interesting example, because in this example, basically you go through the process of problem solving. Okay, you have to make an assumption, test the assumption out, and go back to figure out if the assumption is correct or not. Go back and analyze the circuit again and make a correct assumption. And this is because the circuit doesn't have one mode of operation, it have a lot of different mode. So basically you assume that your circuit behave in one way, then you do the math, you see if it's correct or not, then you go back and you put another assumption on your circuit. Okay, so that's it for today. I'll see you guys later. Okay, so that is our lecture today. Thank you very much, and I'll see you later. Bye bye.